Hi everyone, my name is Natalia Kosmina and I'm a research scientist at MIT Media Lab. Welcome to the last session of the day, actually the last talk of the day. We're going to be talking about using non-invasive brain sensing glasses during zero-G parabolic flight, preliminary study. This work would not be possible without my amazing collaborators, Daniel, Eugene, Chris, Goom, Zoe, and Michelle, so a huge shout out to them. And I also would love to thank our sponsors, NASA, as well as Media Lab's Space Exploration Initiative, for giving us the opportunity to have this parabolic flight happening. Next slide is just a really quick disclaimer. Throughout 15 years of my research career, a lot of companies, nonprofits, organizations are supporting my work, and I'm very happy to be here in Las Vegas. As you can see, I got very inspired by the Sphere, the latest addition to the Vegas architecture, and this whole presentation will be around it. We're going to be talking about brain-computer interfaces in the context of wearable sensing devices, more specifically about head-worn devices, headpieces, earpieces, and glasses. Quite a few of you are actually wearing face masks, I can see a couple of earpieces as well as pairs of glasses. So I'm working on all of those with an important enhancement, which is enhancing all of those devices with brain sensing component, non-invasive brain sensing component, more specifically called EEG or electroencephalography. We either design fully clip-on solutions or we actually design full stack systems. BCIs is a term you might have heard, brain-computer interfaces. I like to call BCI biosignal-computer interaction. What basically it means is that we have a lot of real estate on our head, and we can place electrodes differently in different positions and locations on the head. For example, if you put electrodes on the back of the head, which is visual cortex, we can pick up imagination of objects. For example, you're thinking about getting a glass of a drink for the cocktail that is coming up after the session, or a cup of coffee to wake up. Or you would be paying attention to an object, like visual object. For example, my slides that are actually happening behind me. Or if you're gonna move closer to the eyes or forehead, we can pick up cognitive load and workload of a person. We're gonna put sensors around the ears. We can pick up auditory attention of a person, also known as cocktail party problem. And of course, throughout the years, brain sensing, non-invasive brain sensing was also tested in LEO, so a low Earth orbit. For example, one of the most famous studies, neuroscience study, features their team that was using brain sensing, gel-based brain sensing device, a cap that you would use gel to add to the electrodes. And they even put, actually on, you can see behind me, the black tube on the eyes to prevent subjects from seeing around them, so to have visual distractions. As you can imagine, not the most practical way to go. You would not be able to do this by yourself, and especially in space, that is actually a very complicated task. And of course, throughout all these years, so it has been over 10 years after neuroscience actually took place, ML, AI, but more importantly, hardware is actually moving and evolving on a fast basis. So before, what I usually like to call Natalia in her octopus era, we definitely have only options with multiple electrodes, but now we actually have options where we can wear wearable, truly tiny pieces of hardware that can pick up brain activity. And that might be more than enough for some of the interesting neural markers that we might be looking into. So again, think about if you were to put this tiny wearable sensing device on the astronaut while they are using ARED, while they are actually doing some team building exercises together in deep space, while they are sleeping, or while they are doing science for you in space. And this all could have been done without the use of gel, and they could do this by themselves in under 5 minutes. We have built a device that would enable such type of interactions. We call this suite of wearable devices Attentive View. You can see right now the image of the pair of glasses behind me. This pair of glasses features brain sensing electrodes, EEGs, on the sides of the ears here, as well as EOG on the bridge of the nose. So the device would be worn just like this. Lenses could be added if you're really required to do so. So to test Attentive View among different space analogs, we have picked up parabolic flight, mostly because bed rest is known to introduce a lot of boredom in subjects, and parabolic flights are actually known to introduce some anxiety and excitement, and some activity can happen throughout those flights. More importantly, we were actually interested in seeing any group interactions, or what is also called hyperscanning. Can we use multiple devices to actually acquire the brain activity of multiple flyers at the same time? So our flight happened last year, taking off in New Hampshire, United States, and we have been having 6 pairs of Attentive Views on board with us. This included wearing those Attentive Views throughout whole flight, since the moment of their embarkment till their flight actually landed. So we were able to record brain activity throughout the whole flight, unlike only throughout the parabolas that we usually reported in the previous papers. We have been having our pretty regular 0G flight setup, so parabolic flight setup, with one important enhancement. Unlike a lot of papers, we had an opportunity to also experience Martian and lunar gravities in addition to 0G. What we also were doing is that it's very important to know that all of our flyers, so we had 6 who were wearing the glasses, they had different level of expertise in the flight. Some of them were very experienced flyers, some of them were first-time flyers. One flyer is actually blind flyer. And more importantly, in addition to those 6 flyers, we actually had other flyers, 14 other flyers. And all of those flyers, except one, actually were carrying out their science, so their own project. So they were occupied and taking care how their project is behaving and not interfering with any other scientific project. So that is to be said that each single person was excited, but also a bit anxious and occupied and challenged with their own tasks on board. So this was not just a flight to experience 0G gravity, but also it had some type of workload, important workload for all but one wearers of flyers who were picking up brain activity from. Here is the video from the flight. What you have just seen is one of the 0G parabolas recorded by one of the wearers, one of the flyers on the flight, and you can actually hear and observe that some folks, obviously there is a lot of folks around, they are moving, they are floating when the parabola is actually about to happen, and they're experiencing the 0G gravity. So the approximate duration for each parabola was between 17 to 20 seconds. It's important to note that coming in and coming out of parabola, as you might have heard in the video, was announced by the crew at all times. So we have been recording the attentive view, the signals coming from attentive view using a dedicated iOS application, obviously offline, and then we have been pre-processing the recorded data offline once we go back at the lab. Here you can see just one of the examples of the results. So I do refer to check the paper if you want to learn more, but here you can see comparison between three different gravities: Martian, lunar, and zero. First column, which is yellow, is highlighting the alpha band power, red highlighting beta band power, and violetish color highlights the theta band power. As you can observe, through Martian, now lunar, and finally zero G gravity, we can see a decrease, significant decrease between all three band powers. Here, this is the average for all 6 flyers, average for 20-second duration of the brain activity that we recorded. And this is actually representative for all the flyers throughout all conditions. We were not able to identify any papers that effectively compare Martian, lunar, and zero-G gravities, but we were able to find several papers that compare Martian, lunar to zero, and zero to Martian, and they do stay the same results, so decrease in alpha, beta, and theta activities. To the best of our knowledge, this is the first paper of its kind that was able to record multiple flyers over full parabolic flight, where the flyers were actually experiencing and helping each other, but also doing their own activities and exercises. And this is the first of the paper, to the best of our knowledge, that explicitly compares Martian, lunar, and zero-G gravities. It's very important to note that we had 14 zero-G parabolas compared to 4 lunar and to 2 Martian. This is to say that this amount of data is not equal, and the durations are not equal between 3 parabolas. And in addition to only 6 flyers, all of these results are to be considered preliminary, and more flights need to happen for us to effectively confirm these findings. Thank you so very much for your attention. Again, I just presented you a very quick overview, so please check out the paper to learn more about state of the art and more in-depth results. And happy Halloween, everyone!